right, so here we are. Sorry you're on your own today, but we're going to run through a couple pages in the notes. By a couple, we mean two. And then there'll be two homework assignments associated. Very short homework assignments. This is after you have completed your personal SI lab measurements for lengths and masses and times. Okay, so let's go. Good morning, physics class. Okay, nice to I guess electronically see each other or communicate one way or another. Anyway, let's go on page 15 of the notes. How do triangles model reality? You've already started to see this. You know, we did the flagpole setup, and we still have to wrap that up. But you saw by using right triangles there, we could actually lay geometry on top of the world and make sense of it. So this phrase here, see the right triangle, basically that means look at a scenario and essentially recognize that it would be modeled well by a right triangle. Skipping over example 19, jump down to question 29 for a moment here. Sorry, this says 20, this says 19, a little bit of misnumbering. Anyway, so this is 19 above. You can jump straight down to question 29 for a moment. A 7.5 meter stick is leaning against a wall, making an angle of, with the ground, of 61 degrees. So let's imagine this for a moment. So let's draw a wall. Let's say here's our wall. Here's the ground. And so a stick, let me change the color so we recognize the stick. The stick is 7.5 meters long and it makes an angle with the ground. So here's the ground. 61 is a pretty steep angle. So, you know, if I'm going to put the stick, this is not a 61 degree angle. Maybe something like this, close enough. Even if that's not 60 degrees, it's close enough. It's definitely more than 45, and it's definitely not 90, so it's close enough. So there's our stick, and our angle is right here, our 61 degree angle. And this one's pretty obvious. Wall, ground, stick, there's a right triangle. And so that's kind of the purpose of what we're doing here. So let's back up a minute and let's practice these three, because this is also a skill you'll need to use. So here there are three sub-questions within the example, which is for each of the diagonal lines, imagine it is the hypotenuse of a right triangle and draw its legs. Okay, well that's pretty easy. You know, this one here, you could say that this one is, if I were to put an arrowhead on this, now there is no arrowhead, but if I were to put an arrowhead over here, you would say this line is pointing in two directions. The directions are rightward and upward, so right and up. And so that basically gives away the legs. So let's see, let's draw them actually with dashed lines. And here we go. So starting here, if I come off to the right, how far? Exactly as far as the diagonal goes to the right. So I feel like I'm about lined up right there. That's about just as far to the right. Then I have to go up. How far up? Exactly as far up as the original diagonal. There it is. So what I just drew here are called components. This one down here in blue, this you would call the horizontal. Ooh, shrink that font down a bit. This is the horizontal, or X component. And of course, this one up here, turn it sideways. This one is going to be the vertical, or Y component. color code those. That goes with the red. This one goes with the blue. That's all. Now, this is not the only way to draw these. Notice that I came along the bottom and up the side. Here, you could instead go up first and over second, and you will get an equivalent setup. All right, let's make ourselves a line. Good. Let's make this one red. Good. So this one, we're going to start at the corner and go up. How far up? Just as far as the diagonal went up. So just eyeballing it, that's about right. Maybe it's a little short, but it's close enough. And then it goes off to the side. How far off to the side? Exactly as far as the diagonal. There it is. And so you have your vertical or y component right here. And you have your horizontal or x component right here. Pretty easy, right? And of course, the last one, piece of cake. Sketch them in. I think we're all set. What color are we working with? The blue. Good. We come over just as far as that diagonal went. Don't go farther, don't go shorter. And then you come up just as far, and we could even drop down, as the diagonal went. And there you go. And there's your y and your x again. So I'll color code these, y and x. So pretty easy, right? Duplicate these. This one's the y. This one's the x. So simple as that is, it's actually going to be a very important skill. There it is. And so now, these two together, one thing you should notice up here is that the x and the y are always perpendicular to each other. So put that little perpendicular symbol in there. They're always perpendicular to each other. Therefore, they are together called perpendicular components. So that's a very common phrase. When you hear perpendicular components, what they're saying is you take a diagonal and you break it into a horizontal piece and a vertical piece. Together, the horizontal and the vertical should bring you to the same location as the diagonal. And you say, well, what do you mean by that? Well, if we were to imagine this as an arrow, and by the way, it will generally be an arrow. Let's say you start here, and let's say the arrow ends here. Well, do you see that the solid line, the diagonal path, begins at the circle and ends at the x? The component path, the perpendicular component path, begins at the circle, follow the blue, then follow the red, ends at the x. So in that regard, we say that it is equivalent. The perpendicular components here are equivalent to the original diagonal. They bring you from the same location to the same location. One you might call the shortcut. It's kind of like a displacement. And one you might call the long way, sort of like a distance, which we've talked about. All right, let's jump down to this problem. This problem is old news. We've done this math many times already. So, just speaking quickly, you can come over here, and if you wanted to put in your givens with units, it's a good habit to get in now because you're going to need this all year. We know the angle is 61 degrees. We know that the leg here, we can call these, that's the stick. Maybe we call this A, B, and C. Or, listen, they're talking about sketch the stick and its perpendicular components and determine their magnitudes, which of course, remember we did magnitudes the last day in class or 2 days ago. Just how much, that's it, the value with the unit. Better than calling this A, B, and C, actually would be calling this X. There's the horizontal component. Oh, don't need that. Let's call this Y for the vertical component. And this one I'm going to give you a new name for. Instead of C, I'm going to call that R. And you may say, R, why R? R actually stands for something called resultant, which is basically like the result or the shortcut. But for now, X, Y, and R is a good habit to get into. So we do know that R, or the stick length, is 7.5 meters. And so there are actually two questions hidden in here. They want to know both perpendicular components. So they want to know how long is side y, and separately, how long is side x. These are two separate questions, so don't do them at once. And of course, at this point, you should go ahead and solve these two. This is pretty straightforward math over here. Knowing the angle and knowing the resultant, so these two purple terms, you have the hypotenuse and you have the angle. You can get the adjacent and you can get the opposite. So it's not a bad idea for you to come over here and say, from the perspective of this angle, this is the adjacent side, this is the opposite side, and this is the hypotenuse. It's actually a very good idea to go label that for yourself. And then you'll decide whether it's so, ka, or toa. And so we'll look at one of them partially, and then, it's your job to finish this up. So if we're going to try to solve for y, which is the opposite, well, opposite we need, hypotenuse we know, OH is so. Just as a reminder, the unsubstituted equation looks like this. Sine theta equals opposite over hypotenuse. That is an unsubstituted equation. That gets you the 2-point format. This, SOH, or some other business like this, some shorthand, that's good for you to remember, but that's not going to get you the credit. You need to have an actual equation with the theta symbol and everything. And then, of course, here you're solving for opposites, so you should rearrange this and plug it in, and you get your answers. And I don't have the solutions listed right here. So you go through and run these, and let me just tell you that the answer for doing it right now, the answer for the vertical component should be 6.6 meters, that's rounded. And the answer for the horizontal component should be 3.6 meters, that's rounded. So make sure you get these. Now, this answer is something worthy of consideration too, because clearly the y component is bigger than the x component. Should that be the case? Well, the answer is yes. When the angle is 45 degrees, these two components will be equal. X and y are the same. You get that isosceles triangle. You have 45, 45, 90. But when the angle goes bigger than 45, the y component should definitely be bigger than the x component. So this makes sense. It's reasonable. The homework associated with this is incorrectly marked. Sorry about that. Updating some pagination this year. It's W1.8. And so I'll show you 1.8 briefly. Here it is. It's very easy. 2 sketches and 1 question down here. So here what you see is there's a diagonal, or what we might call a resultant. Here's another diagonal, or what we might call a resultant. And it says turn them into right triangles. We literally just did this in the notes. So sketch them. And then question 2 is calculate, don't measure, don't put a protractor on it, calculate the angle between the vertical component and the hypotenuse. So remember, we name these. We have a horizontal and we have a vertical. So go to the vertical, go to the hypotenuse, find the angle between them using trig. So you're going to do this for each of the diagrams above. That means 2 total calculations. So that's it. That's light work. I'm sure you could finish that during class. All right, let's go over here to page 16. All right, on page 16, what you'll see is how do quadrilaterals model reality. So sometimes we need to see the parallelogram. On the last page, we had to see the triangle. Here, a little less frequently used, but sometimes you need to see the parallelogram. So how do we do it? Here's our example 20, seeing the parallelogram. Frequently what you get is 2 lines like this, maybe both diagonal, maybe one of them diagonal, maybe neither of them. Anyway, what you can do is imagine that this is half of a parallelogram. So you want to sketch in the other half of the parallelogram. Now, what might help you here is to consider that pretend this is an arrow and pretend this is an arrow. As it turns out, these will generally be arrows. Can you figure out what the other side of this parallelogram would be? Well, the easiest thing to do is just mirror the other side. Now, remember the rule of a parallelogram? Rule of a parallelogram is opposite sides are parallel. That's it. Opposite sides are also congruent. But if you just worry about opposite sides are parallel, that makes your life the most easy. So looking at this leg right here, let me call this leg number 1. Looking at leg 1, we'll mirror leg 1 in blue. So looking at leg 1, good, it is moving both up and to the right. So you see the angle of it, the slant of it. Repeat that same leg up here. Don't go straight up. Don't go straight to the right, but go a combination of, oh, I wanted this in blue. Go a combination of up and to the right. You go away. Let's do that again. Dashed, good. Blue, good. So start here. And you can see, this is clearly just up. That's no good. This is up and left. That's no good. This is up and right. This is very right with a little bit of up. This is very up with a little bit of right. Ours looks like it's more up than right. Something maybe like this. And make it too long. It doesn't matter. Move your protractor around and just dash this thing in. It doesn't matter if it's too long. You say, wait a minute, clearly it's too long. It is too long, but watch what happens in a moment. Okay, that's close enough. Now, I'm going to mirror number 2. And we'll do this one in red. Number 2, you see, goes up and to the left. Kind of a similar amount to number 1, just left instead of right. So, let's go over here. Good. Are we red? Nope, now we're red. Starting here, we want to go up and to the left. That's straight up. That's no good. That's straight left. That's no good. This is very left and a little up. That doesn't match what we had. This is very up and a little left. That doesn't match what we had. So what does match what we had? It looks like it's a little more up than it is left. Maybe something like this. Now, do you see? It didn't matter that we made them too long. Where they hit is where the parallelogram ends. Now, this is certainly not perfect. I can see that it's off. I can see that my red one is angled too far down. It's too much left, not enough up. But it's close enough to get a rough idea of what's going on here. So good. Let's do this again with these over here. We'll call this one 1 and this one 2. We'll do the same thing over here. Maybe we'll call this one 1 and this one 2. And so what we're doing here is we are just creating the parallelogram. Now, remember what I said, which is, now use your straight edge when you're drawing these. I'm using the line attachment thing here, the line builder, but you have one of these. So you can come up here. Like 1 is directly to the left on this one. Good. So come up here and draw directly to the left. Take our little tool here. Good. Are we in blue? No, we're in red. Let's put it in blue. Let's go directly to the left. How far? Doesn't matter. Go too far. That's the beauty of this method. Go too far. Now, we need to repeat side 2. Well, side 2 is roughly at this slant. Well, slide your parallelogram, or your protractor rather, over and send it up at the same slant. So let's try this. Boom! That looks pretty good, doesn't it? One more down here. We can start with number 1. Let's see. That's pretty good. Now, we need to repeat that side. Where do we repeat it? Slide your parallelogram. Sorry, I keep calling it parallelogram. Slide your protractor down. We're going to repeat it over here because we're just trying to construct a parallelogram. You see that number 1, if you want to imagine it has an arrowhead, goes very left and a little bit up. So we're going to do that here. Very left and a little bit up. Go too far, doesn't matter. Good. Now we need to reproduce side 2. Let's see how that lean matches. Not that well. Now obviously I'm cheating a little bit because my protractor just keeps the angle. But you can do this at your desk. Line it up and try not to twist it. Just slide it to the left until it reaches the end of that original line 1. Okay. Okay. And now let's reproduce side 2. Boom. There it is. Whoop. There it is. That's not bad. That's a nice looking parallelogram. Okay. The last one, question 20.4, within this example, we need to do a little more carefully. We're going to do the same process that we just did, except now we want to be exact. Now, I can cheat again on this screen because my protractor maintains its orientation. If I turn it this way and move it around, it stays. You don't have that option. You have to be more careful. So follow these steps. There's more than one way to skin this cat, but I'm going to show you the easiest way. This is the way I recommend you do this. This does not frequently appear in testing scenarios, but when it does, it's usually a big 3, 4, 5-point question. And so you want to be ready for that. Here's what you do. Knowing that the opposite sides of a parallelogram are parallel, you also know that the opposite angles must therefore be congruent. Another thing to know about parallelograms, of course, is that your angles are supplementary, adjacent angles. So if this one is, let's say, 50 degrees, then the one over here is going to be 180 minus 50. It's going to be 130 degrees. Now watch what we do with this. Let's measure this angle. This is the way you are going to do this. Do this right now at your desk. Set your protractor crosshair right there at the vertex. One benefit you have is you can actually align better than I can on this. But anyway, that's pretty good. Looks to me like it's hitting on my screen. Now yours may be slightly different. Mine looks like it's hitting at count 10, 20, 30, 40 and a half degrees, right? So I take my protractor, I slide it along that leg until I get to the other end of it. And I align it perfectly, the crosshair right at the end. And there we go. And get the black line over here lined up with that segment. I said 40.5 degrees. I literally come over here and count again. 10, 20, 30, 40. I put a little dot on the outside at 40.5. There it is. Got that? Now, I rotate my protractor and use it as a straight edge. I want to run a line directly from the end of the blue segment that goes through that red dot. And in fact, just like we did before, I don't care how long it is. In fact, make it too long. So let me move this over so I got plenty of protractor here, so I have plenty of straight edge so I can draw this. And so let's say you don't have to write this, but if we call this side 1, we're about to reproduce side 1 over here. So I'm going to make this a dashed line. By the way, you don't have to. Solid line is fine. And I'm going to start here. I'm going to go in the direction of the red dot, and I'm going to go all the way out to the edge of the protractor, edge of the straight edge. Boom. Good. I'm slightly off on this end. You can actually do a better job with paper and a pencil. Okay, good. Now, I'm going to come back over to that same original vertex. Now, originally, we had it lined up like this. And that allowed us to reproduce side 1 up here, down on the bottom. Now we have to turn it. So we're going to turn it so we can reproduce, instead of side 1, we want to reproduce side what we call 2 over here. So I turn the protractor, line this up. There we go. And it should, of course, it's the same dang angle. It should still give 40.5 degrees. Now you could see the thickness of the lines and the problem with using this computer program. Mine actually looks like 41 now. It's all right. Slide along until you get to the end of that leg. Line this up. Now put a dot at 10, 20, 30, 40, 1. Take your protractor, turn it, and use it as a straight edge. Now, I'm pretty sure on your paper, your protractor is big enough to complete this drawing. On mine, it is not. And if that were the case, I'll show you what you would do. So here we go. Let's reproduce now side 2. Start here, go in the direction of that dot, and keep on going. Now, my protractor is too small. What do? Well, you stop, you pick the protractor up, you move it along, and you get it as perfectly aligned to that red line you just made as possible. And you continue your line. Start here and keep going. Sometimes just what you got to do. And mine is a little bit off. And I know you're hearing what I'm saying, which is, I can see that line's not straight, but listen, use your eyes, practice, you'll get good at it, and you won't have an issue. There is a nicely constructed, detailed parallelogram. That's the second piece of your homework. So this, again, misnumbered. This is W1.9. Let me jump over and show you W1.9. Here it is. Questions 1A and 1B. Sketch this so it looks like a parallelogram. Opposite sides are parallel and congruent. Opposite angles are congruent. If it doesn't look like a parallelogram, erase it and do it again. It's very similar to W1.8 for the triangles. Now, on the bottom, this is exactly what we just did in the notes. Complete this one, but do it carefully. You all have a protractor at home, so there's no reason this shouldn't be perfect. Okay, so you'll finish the 2 pages of notes, W1.8 for the triangles and W1.9 for the parallelogram. And then we're almost done with this unit. We'll do the unit test next week. And yeah, we'll get on to some more physics. Good.